Hey guys, welcome to the first chapter of Chem 116. The first 5 chapters of the book, which looks like this. If you haven't seen it yet or hadn't gotten it yet, make sure you go see Shirley. She'll hook you up. But anyway, the first 5 chapters are kind of a general review of chemistry, so that's how we're going to do it. And that's how we're going to do our materials. I'm going to go through the PowerPoints. I will post the PowerPoints after I'm done with them, so you can go through them back again without me babbling if you wish. But I'll go through and give you the materials, and after it can only go 15 minutes. Then after each 15 minutes, then you'll get an assignment. Assignment might be watching a video and answering some questions. It might be looking up some stuff. It might be a quiz, whatever. But you'll get 15 minutes of lecture and then an assignment, 15 minutes of lecture, and so on and so forth. The first couple weeks, we're just going to go through the basics, and then we'll start hitting the organic and the biochem. Okay, so when you're a chemist, you study matter and energy. Okay, matter is anything that has mass and takes up space. Basically, it's anything you can touch, see, or feel. So when you study chemistry, you study just about everything. Okay, now sometimes I ask you, okay, tell me something that's not matter. Well, some people will say air. You can feel air. You ever been outside when it's windy? Yeah, you can feel air. Air is matter. The things that wouldn't be matter would be like your thoughts and ideas, light, electricity, that kind of stuff, okay? All right, if you're looking at matter, matter is found in 3 different states or phases, and I'm sure you guys know, you probably heard these in 2nd grade. Solid, liquid, and gas, it depends on the particles. And when I say particles, I mean atoms and molecules. In a solid, they're really close together. Liquid, they're a little farther apart. A gas, they're really far apart. So how close the particles are to each other, that determines what phase you're in. The other phase is called plasma, and plasma is gas with high energy particles. It's not like the plasma they give you when you're sick in the hospital. To give you an idea, the sun is a big ball of plasma. So plasma is the most common phase in the universe, but not common on our planet. Okay, and then again, you can see, again, just look at the particles really close. That's your solid. A liquid, they're a little farther apart. And a gas, they're really far apart. So these two actually have similar characteristics. These two guys are close together. These guys are way far apart. And again, these particles move as far apart from each other as they can. Okay, so when you're also talking about matter, you're talking about the energy. Energy is the capacity to do work. Okay, we get that from chemical reactions. When you guys eat something, there's a chemical reaction occurs, gives you energy, so you can do things like talk, But there's 2 forms of energy. There's kinetic energy and potential. Kinetic is movement. Okay, so right now, me going like this, I have kinetic energy. Okay, potential energy means the energy is there, it's just not being used right now. Okay, you can actually determine how much kinetic energy you have. You need the mass and the volume. We're not going to determine that, but you can figure out how much kinetic energy there is in an object. Okay, when we're talking about energy, in most cases, especially in chemistry, we're talking about heat. Okay, heat is given off a lot of times in a chemical reaction and so on. But heat is the motion of the particles. The faster they're moving, the more kinetic energy they have, the more the heat they have. Okay, and heat always flows from hotter to colder. And we know this because we have to continuously heat our homes, especially now in the winter. It would be great if heat just stayed where it was at, because once you got your house warm, it would stay that way, but it doesn't, unfortunately. And me, I'm like someone who loves the ice fish. It'd be great if I could just turn on my little buddy, heat up my house, and not worry about it. But the heat wants to go from hotter to colder, so it escapes, and then you got to keep continuously adding more heat. Just think how much money we would save if we didn't have to do that. Okay, temperature is not the same as heat. Temperature is a measure of kinetic energy. So the more the particles are moving, the more the temperature goes up. Well, the heat is kind of a byproduct of that. But when you're taking the temperature, some people think you're measuring heat. No, you're not. You're measuring the kinetic energy. Okay, potential energy is stored energy. Okay, it's there, it's not being used. So like if you have a full tank of gas in your vehicle and you're not driving, there's a lot of potential energy in your gas tank right now. You have the energy to burn that and to move and so on, but right now it's not being used. So the potential is there, but it's not being moved. Or food. Okay, you got an apple sitting in front of you. There is a potential to eat that apple and then use it as fuel, and then you can move and do things. But right now it's just an apple and it's just sitting there. So it has potential energy, but you're not using it. Okay. When we're talking about chemistry, we talk about what they call physical changes and chemical changes. We talk about physical properties and chemical properties, okay? We're talking about substances. Now, when we go through a physical change is where you don't really affect the composition. In other words, what you start with and what you end with, the substance you start with and the substance you end with is the same thing. One of the most common physical changes is a phase change. So if you take you take ice, which is solid water, and you melt it, now you have liquid water. It's still water. So that's a physical change. A lot of times they're reversible. Not always. If I take a piece of paper and I tear it in half, I change the shape of that paper, but it's still paper. So tearing a piece of paper or chopping wood or things like that. Dissolving is another example. If I take salt and I dissolve it in water, some people think that's a chemical reaction. It's not. All I did was dissolve the salt. The salt's still in there. I can tell if I want to taste it, but I don't recommend tasting as a way of doing things in chemistry. It's not a great idea. But I could boil off all the water and then I'd have my salt back. So, that would be an example as well. Chemical change is where you're going to get a change in composition. There's 3 things you can do to tell if you've got a chemical change. Are heat and light given off? When you put 2 things together, does it get hotter? Does it get colder? Is light given off? Another one is, does it bubble or fizz? Okay, like when you put Alka-Seltzer in water, it fizzes and fizzes. You guys probably don't even know what Alka-Seltzer is, but when you put tablets in water and they fizz, that's an example. A gas is being created. That's a new substance. Then I know it's a chemical change. Or another one is something called a precipitate. And a precipitate is like if you have 2 clear liquids and you pour them together and now they're cloudy, that means you created a solid substance that was insoluble. You made a new substance, okay? Another example I have up here is cooking. When you cook stuff, you add heat to it, you change it chemically. Think about an egg, okay? You cook an egg, it's different than when you started. You can't put it back the way it was. So chemical changes, you're going to end up with a new substance with new properties, okay? Now here's an example. What do we have here? We have sizes, okay? When you do measurements in science, and you'll see a lot of times we have a lot of stuff in this chapter, in this book about medicine, because it's this course is kind of more for people that are going into medical fields. But if you look, when you're looking at sizes, here's a single atom, okay? We cannot see that with the microscopes that we have. It takes pretty special to see that. And you can see here's picometers, nanometers, micrometers, millimeters, centimeters, decimeters. We're not seeing anything until about here, in here, okay? But we have a single atom. Again, that's a particle. Here's hemoglobin. Hemoglobin is the stuff in your red blood cell that carries oxygen and stuff and gives it the color. Here's a red blood cell. That we can see under a microscope, okay? It gives you a little bit of the size. A drop of blood, again, there's probably, I think it's like 1,000 of these in one of these. So, big difference. Obviously, we don't need a microscope to see a person. Actually, we can see a drop of blood without a microscope too, but if we want to see what's in the blood, then we got to go to the microscope. So macroscopic means you can see it without a microscope. It's big. Microscopic, you're going to need a microscope. And atomic, those are things we can't see with a microscope. We need special equipment to see those. Okay, so measurements in science, again, when you have a measurement, you have a number and you have a unit. If I just say there was 6 what? 6 seconds, 6 hours, 6 millimeters. You need a unit so that you can, it clarifies what you're talking about, okay? When we talk about the systems that we use for measurements, okay, in the United States, we use the English system, which is weird because nobody else uses the English system but us. Even the English don't use the English system. The English system is inches and feet and yards and miles and things like that. The metric system, or they'll call it the System International, is meters, liters, grams, things like that. And, if you take all the people in the world, there's like 8 billion people in the world, 7.8 billion people use the metric system. A very small portion of the universe, the population, uses the English system. So in science, we always use the metric system. 2 reasons. First of all, it's way easier to use. When you convert, all you do is like multiply by 10, 100, 1,000. You just move the decimal a little bit. You think about the English system. If you go from inches to feet, there's 12 inches in a foot. but there's 3 feet in a yard and there's 5,280 feet in a mile. It's not a very good system. It's not very convenient to use. Whereas the metric system, everything's based on units of 10. So it's much easier to use. And the other reason we always use the metric system is if you did research in science and you published your paper, you want the most amount of people to understand it. There's way more people that use the metric system than the English system. And scientists in the United States use the metric system, so that whenever you're doing anything with science, you use the metric system. You never use the English system. Okay. So again, in the metric system, we have base unit, the meter. The meter is 39 inches. It's a little bit more than a yard. The gram is for measuring small units of mass. A penny is a couple grams. Okay. A second, that's nice. Everybody uses a second. A calorie is for measuring energy. Okay, and like the calories on your food and stuff, okay? And then you have prefixes. And like I said, right here would be where your base unit would be. And you can see how it goes by tens, hundreds, thousands, whatever. It's really easy to convert from one. All you have to do is move the decimal around. So the metric system is way easier to use than the English system, okay? The prefixes are used when a measurement is small, and then you use larger units. So let's say you're going to measure, here we got a millimeter. Okay, we're measuring a small unit. Most of the time when we measure stuff in chemistry, we use a centimeter. All right, where we would use inches, we would use a centimeter. Okay, and there's like 4 centimeters in an inch. About that. No, I lied. There's 2.54 centimeters in an inch. I said that wrong. Sorry about that. And then here's a decimeter. We don't use decimeters. Most of the time when we're measuring length, we use millimeters for really, really, really small. We use centimeters like we'd use inches. Where we'd use feet, we'd use a meter. Okay. And then we're talking about really long distance, like miles, we'd use a kilometer or a kilometer, whichever way you want to say it. Okay. All right. Length, again, a meter is the base unit of length. So if you get smaller, decimeter, millimeter, centimeter, those are smaller units than a meter. And again, a meter is a little bit more than a yard. A meter would be like where we use feet or yards. And then if you need a really big unit, you'd use a kilometer. But there's also other units in between there. Okay. When you're talking about mass, mass is how much matter you have. That's what you get from the scale. Okay. When you step on a scale, you're getting your mass. Okay. So the base unit of mass is a gram, which is kind of a small unit. If we were using, like we would say pounds, we'd use a kilogram. Okay. There's 2.2 pounds in a kilogram. Those of you that have ever wrestled or weightlifted or anything like that, your weight classes are based on kilograms. Okay. Volume is how much space something occupies. And that would be a liter. Okay. We know a little bit more about liters. We have 1 liter bottles and 2 liter bottles and things like that. And if you look at all like pop cans and they have the liters on there as well. 12-ounce pop can is, I think it's 455 milliliters or something like that. So there are some conversions on the containers. Okay. And again, when we talk about energy, we use a calorie. A calorie is how much energy it takes to raise the temperature of whatever. Temperature, 1 gram of water, 1 degree. So if you're burning something, you're going to absorb that energy and see how much it raises the temperature. And again, calories is like what you see on your food and the little labels and stuff. Okay. Well, I hope you can see this. Okay. When you're taking measurements, this is going to be our last slide, you guys. We're going to run out of time. Sometimes I run out of time. You have to forgive me. I'm just not, I forget. Anyway, precision. Oops. So okay. Precision is how close are your measurements to one another. Let's say you're doing an experiment and you do 10 trials. You got to look at your numbers and see how close they are to each other. If they're not close to each other, you weren't very precise. Something happened and you weren't taking very good measurements. Accuracy is how close are you to the right measurement. Now, one thing you have to have for accuracy is you have to know what the right answer is. But ideally what you want to be is precise and accurate. It doesn't always happen. In here, they're showing you some of they're all around the same number. So these were very precise. And the right answer is 7.5, so they're very accurate. Here, they were precise. They got 8.1, 8 and 8.2, but the right answer is down here, so they weren't very accurate. Here, they were all over the board, not very precise. And here, again, they weren't near the right answer, and they weren't very precise. Another way they'll show this is through a dartboard. If you hit the bullseye with all three, you're accurate and precise. If you hit all three in an area that's not the bullseye, you were precise but not accurate. And then if they're all over the board, then you're not neither. Okay. And we're done.